Hello everyone and welcome to another lecture of Survey of Physical Sciences. And in today's lecture, we're going to discuss, at least for chapter 2, we're going to discuss about motion. Motion is a very general concept in physics, and we are going to break down this concept into smaller ideas such as speed, acceleration, velocity, force, and so on throughout this class, okay? But just so you know, to give you this general idea of what we're going to talk in this class, is that motion is the movement of a object, as you can imagine, right? Is the change in the position over time of that object. And for that object to be moved from position 1 to position 2, it is required that a force to be applied onto that object, okay? So, very basic concept is that motion is the movement of this object, of the matter, right? And that movement occurs throughout time. And for that movement to occur, we need to apply some sort of force. And that force we're going to study is proportional to the mass of that object, okay? So let's think about a very simple example, all right? Let's think that you have a ball in your backyard, okay? And then this ball, you check around lunchtime, you check and the ball is in the middle of your backyard, okay? A few hours pass by throughout your day, you go to school, you come back, and then you realize, you observe, and then you see that the ball that was once in the middle of your backyard is now at the edge against the fence in your backyard. And that is already evening when you got back home. Okay? Here, I described two important aspects, or I needed to inform you two important aspects for you to understand what happened with that object. I described what happened to the position, which changed, right? It was in the middle of the backyard and then it was against the fence. And I also gave you a notion of time, right? Because I told you that when you were there, in the afternoon, you observed the ball in the middle of the backyard, but then in the evening or at night, when you came back, you observed that the ball against the fence. So two things were necessary here for you to understand what actually happened to the object, what happened to the position, and what happened to the time during the day, okay? And combining these ideas, we can describe motion using three main aspects, three main concepts, and they are speed, velocity, and acceleration. Those three aspects, those three concepts, they combine position and time in some way, manner, fashion, okay? We're gonna use this concept of changing position over time to apply these ideas to horizontal motion of objects and also to falling objects. Later on, we're going to see how we can apply these concepts to ideas such as force, which is the first law proposed by Newton. Then we're going to talk about inertia and its relation to mass. We're also going to talk a little bit about the law of gravity, which will give us a little bit more of an application of how this motion can be understood in a more complex system, okay? Before we keep going into these ideas and how to calculate those things, I want to start defining two important concepts here for this class. One is scalar, and the other one is vector. A scalar is a quantity that only has a magnitude, that only has a size, okay? Whereas a vector is a quantity that, besides of having a magnitude, also has a direction. And that direction can be from left to right, up and down, okay? Scalar, you only have a number that describes the size of the matter, okay? For instance, what are some examples of scalar quantities in physics? Mass, distance, speed, volume, temperature, and energy. You don't need to know the direction to know what's happening with the mass, right? If I tell you that I weigh 65 kilograms, that number itself is good. You understand what that number means, okay? If I tell you that my car, I am driving my car at 55 miles per hour, you also know what's happening, what is the average speed of my car. However, there are some quantities that we need to indicate the direction. For instance, yeah, it's fine that I tell you the average speed of my car, that is 50 miles per hour. But if I tell you that I am going north, I am also giving you a direction. So now I am transforming this quantity that was scalar into a vector, because I am giving a direction to this quantity, to this number. I am indicating that I am going from one place to the other in a certain direction and not the other way around. Okay? What are some examples of vectors? They can be position, displacement, velocity, and acceleration. They are usually represented with a vector notation, which is a arrow over, which is a arrow over the symbol that we are working with, okay? Those quantities can be represented by positive and negative signs, all of them, okay? And that positive and negative sign will indicate what is happening with that quantity. I know that this seems a little bit abstract, but I promise you that it will make sense as we move on in this class, okay? All right, let's start describing motion from its very basic concept, okay? Let's look at this example. The car here, the car is traveling a distance of 150 kilometers in total. And that car has traveled these 150 kilometers within 3 hours. Same thing as the ball moving in the lawn, in the backyard, okay? I told you where the ball started, where the ball ended. I told you the initial time, and I told you the end time, okay? Same thing here. When I look at the motion of this car, I can see that there was a change in the position of the car and that there was a change in time. The change in the position, we can call this d, okay? And d stands for distance, all right? And changing time, we can call this t. Sometimes you will see these two letters accompanied by a delta sign. That means variation, okay? Knowing this, or that is to say that I can calculate what happened to the distance of this car over a period of time. When I calculate the distance over time, I have what we call speed. Okay? So speed tells us what happened to the position over time. Okay? To calculate speed, this distance, we will need to know the final distance minus initial distance. And same thing for time. We need to know the final time minus the initial time. And that's why I told you that these can also be represented with a delta, okay? The delta means change. Delta means a subtraction between final minus initial. So we can say that speed equals to delta d over delta t, okay? This speed that we are calculating is the average speed. So when I tell you that I drove 50 miles per hour, I am telling you my average speed from my house to the Carolina University, for instance, okay? To represent the average speed, we can also use a delta symbol next to the S. Speed in the metric system is given in kilometers per hour or meters per second, okay? We are not going to use miles per hour. I know you guys are used to it, but that's not what we are going to do here in this class, okay? I also want to tell you that there is a conversion that is very important here in this class. I can convert from kilometers per hour to meters per second. And to do this conversion, I need to divide the number by 3.6. To convert from meters per second to kilometers per hour, I need to multiply by 3.6, okay? And you can wonder, why is that the case? Very basic, is because 1 hour has 3,600 seconds, okay? And 1 kilometer has 1,000 meters, okay? If you divide one by the other, you have 3.6. And that's the conversion factor that we are gonna have. All right, can we do the example of the car? Let's calculate the average speed, the delta S, okay? How can we calculate the average speed, which can also be represented by the V with a dash on top, with a bar on the top, okay? How can we calculate this? Well, I know the change in the distance, right? I know the change in the distance, or the distance traveled by my car, is 150 kilometers, okay? How about the time? I know the time that has elapsed from the moment I started driving in this trip was 3 hours, okay? So, to calculate the average speed, we can divide 150 kilometers over 3 hours, and that will give us 50 kilometers per hour. Professor, but is there a different way that I can calculate this? Yes, there is a different way that we can calculate this. Let me do this. Well, look at how we can calculate this. Remember that when I said the delta D represents the final distance minus initial distance. Well, what is the final distance here? 150. What is the initial distance that we started? 50. So I can also say that delta D, if I want to go for this way, is 100 kilometers. Okay? How about the time? I know that time can be given by time final minus time initial. Final is 3, initial is 1. 3 and 1. I know, therefore, that my delta T is 2. If I apply in my formula, I also have the same answer, okay? Delta S, or my average speed, is 50 kilometers per hour. And why is that the case? Why can I calculate doing both ways? Well, because physics makes sense, right? You can do both ways. That's the basic answer I can give it to you. It just makes sense. I have another example, and I want you to pause right now and try to do this example on your own. But I'm gonna do it with you. So we have a driver of a car moving at 72 kilometers per hour, and this person drops a road map on the floor. It takes this person 3 seconds to locate and pick up the map. I want to know how far in meters this person traveled during these 3 seconds. How can we calculate that? Well, let's start by separating what kind of information we already have. We know the speed, and we also know the time, okay? So I can say that the average speed of this car is 72 kilometers per hour, and the time that has elapsed is 3 seconds. There are many ways to solve this question, okay? Feel comfortable to solving this question however you want. I want to know basically the distance that the person traveled, but in meters, okay? I know that my equation tells me that speed is delta d over delta t, okay? Rearranging this equation, I get that delta d is the same as delta s times delta t. But here's the thing. My speed is in kilometers per hour. My time is in seconds. And I want to know my answer in meters. How do I do that? The easiest way is converting the 72 kilometers per hour to meters per second, because bringing kilometers per hour into meters per second gives me the same unit, okay? So let's do this. So to convert 72 kilometers per hour into meters per second, I need to divide by 3.6, okay? Let me do this on my phone. You guys can use your calculator. I don't care about it. Doing 72 divided by 3.6, you should find that this velocity is 20 meters per second, okay? Well, now I can plug in my formula. I know that speed is 20 meters per second, and I know that time is 3 seconds. Look what's going to happen here. I have second dividing and second multiplying. I can cancel them out. So now I am left with 20 times 3, which is 60. And how about the unit? Meters. So I know that during those 3 seconds, this guy traveled a distance of 60 meters. Okay? Again, there are other ways of solving this equation, and I don't care which way you solve it, okay? As long as we get to the same answer and your, thinking actually makes sense, I really don't care how you get to these numbers. I told you that speed describes the change in position over time, right? And I told you that speed is a scalar type of measurement. How about velocity? Velocity and speed sometimes are used interchangeably. However, they are different because speed is a scalar magnitude and velocity is a vector magnitude. Okay, so velocity has not only a size but also a direction. Okay, so velocity not only describes how fast the car is going or the object is going, but also the direction to where the object's going. Okay, so if I tell you again that I am driving 50 miles per hour, well, that's my average speed. But if I tell you that I am driving 50 miles per hour from Greensboro to Winston-Salem, that gives you a direction from where I am going. Okay, so here we can represent this vector with magnitude and direction. Okay, these vectors can be represented with arrows. The length of the arrows describe the magnitude. Okay, and the arrowhead to where this arrow is pointing describes the direction. All right, we can also represent this velocity in a graphic form. Okay, I have a graph here where x is the position and x is the time and y is the position. Okay, looking at this graph, I can understand what's happening with the velocity, what's happening with the position, and what's happening with time for this object that we are analyzing. My first question I have for you here is, what was the average velocity of the object from t0 to t9 seconds? Okay, I want to know the average velocity from time 0 to time 9. How can I calculate this? Remember, we can say that velocity is change in distance over change in time. Okay? I can also open what these changes means. I am saying that I have a final distance minus an initial distance over a final time minus a initial time. Let's look at it. What is my final distance at 9 seconds, which is my final time as well, right? My distance, as you can see, is 0. So my final distance is 0. How about my initial distance? Where did I start my car or that object? At 1 meter. How about time? Time finished at 9 seconds and started at 0 seconds. So the average velocity here is minus 1 over 9. What are the units? Meters per second. My students, when they see this negative sign, they go crazy. And they think they did something wrong and they got the exercise wrong. Did they actually got this exercise wrong? Or this is right? What do you guys think? It is right, okay? What is this negative sign telling me? Why do I have a negative sign? And why is this correct to have a negative sign? The negative sign is telling me that I moved sort of backwards in time, okay? Look, I started at position 1 meter, and then I started at position 1 meter, and then I finished at position 0. So I kind of moved backwards, right? I didn't move forward in time. I moved backwards, or moved not in time, but I moved backwards. Instead of stepping forward, I moved backwards, right? So that's what the sign means. And that's why I have to represent this average velocity with the V and a bar on top of it, because there is a direction, okay? There is another question here. What was the average velocity of the object from time 4 to time 9 seconds? How can I calculate this? And while you guys are trying, I am gonna erase all that. All right, very good. Do we have an answer? Let's do the same thing. So, velocity is delta D over delta T. Delta D is final distance minus initial distance, and delta T is final time minus initial time. Okay, how can I calculate this? What are the numbers I should plug in? Let's look at it. So from time final I know that is 9 seconds, but the distance at 9 seconds is 0. Okay, what about the initial distance, or the distance at 4? The distance at 4 was 3. How about time? Time would be 9 minus 4, correct? This should be minus 3 over 5 meters per second. Okay, again, I have a negative sign, but do not worry about this negative sign, because the negative sign is telling me that I am moving backwards. Okay, instead of moving forward, I am moving backwards. Okay, that's why we can say the average velocity is minus 3 over 5. Does that make sense? I hope so. Another way of describing motion is using acceleration. Acceleration will define the rate at which the motion was changed. That's kind of complicated to understand, right? Maybe not. I am simply saying that acceleration is telling me how the velocity changed. What is the rate of change of that velocity over time? Okay? Saying rate over time, it's kind of a redundancy, because rate means something over time. So I was kind of redundant in my phrase now, but you get what I'm trying to say, right? And that is because the speed can change, the direction can also change, and both speed and direction can change together, okay? For instance, let's say that I started driving from Greensboro to Winston-Salem at, 50 miles per hour. When I finished driving to Winston-Salem, my average speed was 100 miles per hour. Let's say that I sped up so much. That means that I accelerated over time, okay? From 50 miles per hour to 100 miles per hour. How do we calculate this? Using our formula shown here. Okay, acceleration is velocity over time. The unit for acceleration will be meters per second squared. All right? And that is important for you to know. I have one example here. So let's consider a car that is moving with a constant velocity of 60 kilometers per hour when the driver accelerates to 80 kilometers per hour. So I am telling you that the guy is accelerating. Suppose that it takes 4 seconds for this driver to increase the velocity. So what was the acceleration? What was the change in velocity over time? How can we calculate that? Let's begin by noting what we have and what we want to find. Okay, so what do we have here? We have the initial velocity, which is 60 kilometers per hour. We have the final velocity, which is 80 kilometers per hour. We also have time, okay, which is 4 seconds. I am already telling you that it takes 4 seconds. You don't need to express the initial time was 0 and final time is 4, because I am already telling you that the total here was 4. Okay, so delta t is 4. But here's the thing. I am giving you the velocity in kilometers per hour. The time I gave you in seconds. And I want to know the acceleration, which is delta v over delta t. Acceleration is in meters per second squared. Oh my goodness, how do I do that? The easiest way for doing this is converting these two guys to meters per second. Okay, so how do I do that? Kilometers per hour to meters per second, we need to divide by 3.6. Okay, and we can all use our cell phones now to calculate this, but this should be 16 point, I'm gonna approximate here, 16.67, and this should be 22.22. Okay, so now we plug in our formula that tells us that acceleration is distance over time. Acceleration is final distance minus initial, not distance, velocity, sorry. Final velocity minus initial velocity over delta time. Final velocity was 22.22 minus 16.67 over 4 seconds. Great. What is acceleration now? It should be 1.4. I'm also going to approximate 1.4. What are the units here? Meters per second squared. Okay? You can prove to yourself that it's meter per second squared because you have here, this is second, you have meters per second here, you have meters per second here, okay? And then by doing the transformation with these values, you can get that the final result will be meters per second. All right? We can also represent this relationship between change in velocity over time by using a graph, a graphic representation, right? So in this graph, we have that the y-axis represents velocity, and the unit for velocity is meter per second. And then the x-axis represents time in seconds. And we know that the slope of this graph represents acceleration of the object. Remember that acceleration will always be the velocity over time, okay? And this is given in meters per second squared. All right, so a quick question for you, and think before you keep watching this video. According to the graph above, what is the object's velocity at time 4? Time 4 represented here. Think about it. Well, if time is 4, then if I go up here, I can see that the velocity, and I can represent that by the velocity at time 4 seconds equals to 3 meters per second, okay? All right, here's another example of how to understand or how to interpret the slope of this graph. So let's look first at this question. At what time or times did the object have a velocity of 0? When you look at this graph, where in this graph do you see that the velocity was equal to 0? Remember, velocity is represented in the y-axis and time is represented in the x-axis, okay? Where is velocity equal to 0? At time equal to 6 seconds. All right, that's when the velocity is 0 according to our graph. The other question I have here is, during what time interval was the object moving in the positive direction? Well, let's think that. Positive direction we can also associate with moving forward. Negative direction means moving backwards, okay? Let's just make it as simple as this. So that's what I'm asking, when velocity was positive, okay? And I could also ask when velocity was negative. Looking at the graph, velocity to be positive has to be above the x-line, because when velocity is below the x-line, then velocity is negative. So the answer to my question is, what is the time interval from 0 to 6? The velocity is positive, because after 6, velocity starts to be negative. Okay, so we can say that time from 0 to 6 seconds, the velocity is positive. Okay. All right. What the other question is asking me, is the object speeding up or slowing down at time 4? So let's look at time 4 here. Okay, which is right there. Velocity is this. Okay, 3 meters per second. All right, what's happening with the velocity? What's happening with this object at time 4? Well, how do I get to this answer? Let's look at what's happening with acceleration, right? Acceleration is the slope in this graph, right? Acceleration would be the rise over run in this graph. We can see that, and let me remove some of the ink here because it might get... Okay, we can see that at time 4, the slope is negative. If the slope is negative, that means the acceleration here is negative. If the acceleration is negative, the car is slowing down. The car or the object, okay? Okay, at time 4, this object is slowing down because I can see that the velocity, even though the velocity is positive, the acceleration is negative. Okay, and you can calculate that it is negative by using our formula if you want to try to prove it to yourself. But just look at the slope. The curve is going down, so you can deduce that you can conclude that the acceleration is also slowing down. All right. Next, to finish this part of speed, velocity, and acceleration, I want to show you this graph. We can also calculate the displacement of the object by calculating the area under the curve in a graph where you have the velocity in the y-axis and the time in the x-axis. Okay, so we know from our formulas that velocity equals to distance over time. Okay, by doing a cross multiplication, I know that distance equals to velocity times time. Okay, look at this. Velocity in this graph is constant, right? It does not change. So velocity here in this graph is 6 meters per second. How about time? Time, delta t, was from 0 to 5. So I know that delta t is 5 seconds. Whoa, look at this. D is, you cut the s's, and now what you have is 6 times 5. This equals to 30 meters. Okay? That is the same thing to say that this is a square, And if I calculate the area of this square, how do I calculate the area? Isn't the area side times side in a square? If one side is 6, the other side is 5, then I know the area is 30. How about the units? Well, cross the time, and I am left with meters. Okay? Continuing in this idea about motion, I want to talk to you about force because, when I said that to cause this change in the position over time, we need to apply a force to move that object, to actually change the motion of that object. So force we can understand as a push or pull that's capable of changing this object's state of motion, okay? The overall effect of that force will be determined by what we call the sum of all forces acting on that object, what we can call as the net force, okay? So for instance, in this example here, we have a big battleship or whatever type of ship we have, okay, a big boat, all right? So here, if I have two forces applied in the same direction, then the net force that will make this boat move forward is simply the sum of those two forces together, okay? So the boat moves forward. However, look at in the second example. Now I have one force acting to move the boat from east to west, and one acting to move the boat from west to east. They are both similar in magnitude. They are just different in direction, okay? However, as you can imagine, those two forces are opposing to each other. Therefore, the net force acting on this object is equal to 0, okay? The third example is just a repetition of what I just said. So here you have two forces. One force moving to east is smaller than the force moving to west. So the net force acting on that boat will move the boat to the west with 1,000 units of force, okay? So force is important because it will govern many things that we can observe in nature, such as the gravitational force between the masses, between the planets. So for instance, there is a gravitational force between the sun and the earth that keeps the earth in orbit, right? The electromagnetism is also a type of force, okay? And we are gonna study that in the following classes. But just coming back to this idea that to move the object, we need to apply a force on that object, and actually describes this principle of inertia, okay? Because the object will not move if the force applied to that object isn't strong enough to move that object, okay? So inertia is this property that describes the tendency of this object to resist a change in its position, okay? If the force applied to this object isn't strong enough to move the object will stay steady without moving, okay? So we're going to discuss a little bit more about inertia when we discuss Newton's law, but I just wanted to give you a general idea, because this idea that there is a force acting on the objects will actually guide some thoughts about why the objects are falling, right? Why do objects fall to the earth, right? Reaching the earth's surface, okay? Aristotle, which was one of the first philosophers to think about why objects fall towards the earth's surface, it's because he thought that, these objects, they have a mass, and the heavier the objects, the faster they will fall. But Aristotle doesn't actually did any experimentation to prove his point, okay? He was more of a philosopher, so he only relied his explanations in thinking. It wasn't until actually Galileo and Newton that we actually have an idea for why and how these objects are falling towards the Earth's surface, okay? These two guys, they will say that all objects, no matter their masses, they will fall at the same rate. And remember that rate here, we're going to call this rate acceleration, which is the change of velocity over change in time, okay? So they observed that no matter how heavy that object is, they follow at the same rate. Okay, and their reasoning was based actually on certain measurements. So let's calculate this rate together. Can we do that? And you will see that this rate that I'm talking about, it is actually the gravity. And gravity is a type of acceleration that pulls the objects towards the Earth's surface. Okay? So in this object, what we can observe is that the distance. So imagine that I am right here at the top of the Empire State. Let's pretend that this is the Empire State Building. And let's say that I am dropping this ball from the very top of the Empire State. Okay? I, as an observer, I see that the distance as the object is falling in free fall, disconsidering the resistance of air, as the object is falling, I see that the distance reached by this object every second is proportional to the square of time of the fall. Carlos, what is that? What did you just say? Well, that means that in 1 second, my object actually reached 4.9 meters in its free fall. Knowing that initial distance in 1 second, I can predict what is the distance this object will reach after 4 seconds. If I know that the distance is proportional to the square of time, time here will be 4 seconds. The square of 4 will be 16. Okay? I know, therefore, if the distance is proportional to the square of the fall, and I know that I started at 4.9 meters, therefore I can multiply that by the square of the time, and I get that this is 78.4 meters. Okay? With that, they observed, especially Galileo, will observe that the velocity of this object that's in free fall increases as the object falls. And if the velocity is changing over time, I call this acceleration, right? And this acceleration, as you can imagine, if the object is falling down, this acceleration is actually the gravity acting upon that object. Okay, so we can say that the object in free fall is accelerating uniformly towards the surface of the Earth. And they came to the conclusion that this acceleration is of a value of 9.8 meters per second squared. And we know that the gravity acceleration is that value. How do we get to this value, you can ask to me. Let's start with a very basic simple idea, actually. Okay, can we do some math here? Let me do this. Okay, let's look at this. I know that I want to prove you that the gravity acceleration is actually 9.8 meters per second squared. Okay, that's what I want to do, and how Galileo got to that number, that gravity is accelerating, is changing the velocity of that object in free fall at that very rate. Let's start with a very basic idea here. I know that acceleration is the same as velocity over time, correct? I can say that acceleration is therefore final velocity minus initial velocity over time, okay? I also know two things here. I know that average velocity is given by distance over time, okay? But average velocity can also be given by final velocity minus initial velocity over 2. Why is that the case? Well, you can say that 100 plus, let's say that in a school, I have one student and their score in the exam is 100, okay? Student number 1. And I have student number 2 and their score is 50. If I want to know the average score of that class, I can do 100 plus 50 over 2. And I get that 150 over 2, that is equal to 75. So 75 was the score, average score of that class. With the same principle, I can also say that average velocity is final minus initial over 2. Okay? Oh, sorry, final plus initial, sorry, following this principle here. Okay, let's now kind of put this in a big equation, okay? I can say that average speed can be calculated using two ways. I can say the average speed can be calculated d over t, but also this, like this, final velocity plus initial velocity over 2, okay? Let's organize things here. Can we do that? Can we organize these things? I need to include acceleration here, right? I need to include acceleration. How can we include acceleration here? Well, let's look at this first formula that I have here. I have that acceleration is final velocity minus initial velocity over time, okay? I have one term here that I can replace, right? I'm gonna work with initial velocity here. So I wanna replace this final velocity because initial velocity is just easier because most of the time initial velocity will be 0 in our examples, okay? So how can I isolate final velocity in this formula here? I can do acceleration times time equals to final velocity minus initial velocity. I can say that final velocity equals to initial velocity plus acceleration times time. Okay, now let's replace this in this big equation. Okay, I can say that d over t equals to vi plus at plus vi over 2. Ooh, now it's getting a little bit more complicated, but look, I have two vi's. Okay, so what I can do is actually write this in a better way. How about this? Let's make things less complicated, okay? I think that sounds good. If I have, this is also as the same as this, over 2 plus at over 2. If I have 2 here, I can cancel. So I have d over t equals to vi plus at over 2, right? Look, I have t on both sides. I need to cancel those t's. So I can cancel by moving the t to the other side, and that would be my equation. I can multiply the equation on both sides by t, right? So that's going to be d equals to vi plus a t times t is t squared over 2, okay? So I know that my distance is proportional to all this equation, okay? But Carlos, you still did not answer me how they got to 9.8 meters per second squared. Well, let's use the example that was in the book. Can we do that? Keep this equation in your head. I'm going to go back to this. I'm going to go back to this example here. Okay, so let's look at this. So I know that I'm going to write my equation here. Distance equals to vi plus at squared over 2. Let's use this guy over here, okay, which is my final distance. I'm just going to use that one, but you can use whatever you want. All right. My final distance is 78.4, okay? My initial velocity when I was at the top of the building holding the ball, the initial velocity here was 0 meters per second, right? Because I was holding the ball. So the ball is not moving, it's not changing its position, so it's 0. So I can say that the VI is 0. Let's get rid of that VI. So now I have A. What about T? T is 4, right? Because it took 4 seconds for the ball to reach this position. So it's 4 squared over 2. So that should be 78.4 equals to 16A over 2. That should be, what? That should be, let's do like this. Let's do 16A equals to 156, right? Am I correct? I guess. A equals to 156 over 16. A is, I need my phone now because I can't do everything on the top of my head. And I get that 156.8 divided by 16. Whoa, look at that. It's 9.8 meters per second squared, right? Why is it squared? Because time was squared, and then I just carried meter right here. So this was already squared, okay? So by a simple, or maybe not so simple like this, by a simple assumption, right, with some of the equations that we already knew, we can actually say that the acceleration, the rate at which the objects are falling towards the Earth, the surface of Earth, is actually equal to 9.8 meters per second squared. And that is the gravity, the acceleration of gravity. Okay, let's do one example. Okay, we have this, that a rock is dropped into a well and hits the water in 3 seconds, ignoring air resistance because we're working with free falling objects. Okay, how far is the rock to the water? So it's the same principle here. I am at the very top here of the well, and I am dropping this rock down into this well. I want to know, I'm telling you, it takes 3 seconds for the water to hit the well. I want to know what is the distance of this, between me and the well. So what is the distance? How far is the rock from the water? Well, I can use my formula, right, that I just got. So I got that the distance, I got that the distance is actually the VI times AT squared over 2. But VI, remember, the rock is, there is no motion, right, because I'm holding the rock. So this is actually 0. So D is A times T squared over 2. So D should be, what is the acceleration? I know the acceleration is 9.8, right? Because it's the gravity that's pulling the rock towards the surface of Earth or of the well, right? And then I do times time, which is 3 squared over 2. Now I'm gonna use my phone because I just can't do all this math, right? So it's 9.8 times, there should be 9. So this should be 88.2 over 2, and we can see that the distance is actually, that's 44.1. What's the unit here? Meters, right? Because I had meters per second squared. Here I had second squared, so I cancel these two. So my final unit is actually meter. All right, so how far is the rock to the water? You can say that the rock to the water is actually 44.1 meters distant from each other. Okay, now continuing with our study of motion, there are 3 types of motions essentially. We've been talking about the vertical motion, which is, we just talked, about the vertical motion, which is when the gravity acts on that object. We also talked about the horizontal motion, which, was my example of the car moving in the horizontal position, but there could be this compound motion, which is actually the combination of the vertical motion and the horizontal motion. And we are going to see that in a projectile motion, okay, which is when you throw the object in the air. You see that the object will, start in a straight projection and then slowly go down towards the, surface of Earth, right? And that's because the gravity is acting on that object at all times, and that's why it makes that curve. But this gravity, is the acceleration to which this object will fall towards the surface of Earth. All right, so let's look at one example in terms of vertical motion. Okay, so here, for instance, you have a little kid on the tree that drops the ball. Okay, we know that there is an acceleration that's pulling the ball towards the surface of Earth, right? And that ball is accelerating at that rate of 9.8. Let me just put it here, 9.8 meters per second squared. We just talked about how we got to this value, right? So you can see that as, the object is falling, the object is accelerating downward, okay? Here, on this other example, I have a guy that's, throwing the ball up and then the ball is falling down. You can see that as the ball is going up, the ball starts slowing its speed, right? And that's because the acceleration of the gravity is acting upon that ball, right? It's pulling the ball towards, again, the surface of Earth. So here, there's going to be a moment where the velocity is 0 for this ball, and then the ball will start moving towards, again, downward, okay, because of the gravity acting on that object, okay? Now, how about this type of projectile motion? Here you can see that these people are, shooting the arrow in the air. If we neglect that the air is actually, promoting any resistance to the arrow, we are going to see that there are two types of motion occurring with this object. There is one that is the vertical motion, which is, proportional to the acceleration of gravity, but there is this horizontal motion, right, which is the same if there is no air resistance, if we neglect the air resistance here. But as the object, is falling down, you can see that the velocity here is increasing, and that is because it is accelerating at the rate of gravity acceleration, okay? And then it makes this curved path that you can see because there's gravity acting upon that object, okay? And that's because, we're gonna start talking about the three laws of motion that were postulated specifically by Newton, okay? And this guy, received a great attention because his ideas were actually proved with calculus, essentially, right? He was able to not only hypothetically think about it or, make a theory about it, but, he proved mathematically of what he is speaking about. Okay, so let's talk about the very first law of motion that he proposed. So the first one we covered a little bit in previous slides, but is the law of inertia, right? So I told you that that object that will only change its motion state if there is a force acting on that object, and that force is actually unbalanced. So you're putting a higher force than that object has, and then you are moving the object whatever direction you are moving that object. Okay, so the most simple definition of this law is by saying that every object remains at rest or in its state of uniform straight line motion unless there is an unbalanced force acting upon that object. Okay, so this object will stay stopped if there is no force, but if the force is strong enough to move that object, the object will move as well. Okay, so you'll probably experienced that when you were probably driving and then you have to slam on a brake. Hopefully you were very careful about that, but when you slam on a brake, you see that your body keeps kind of moving forward, right? And then the seatbelt kind of pushes you back, and that's because you were in motion, right? You were moving forward, and then you applied a force to brake the car, right? And then that acted against the force that was making you move forward, right? So when that happened, your body, who was already moving, had another force acting against it. And that's what the idea of what inertia would say, right? So the object will only change its motion if there is a force that's acted, that acts on that object, all right? That's very simple. The second law of, motion proposed by Newton actually describes that force, this force that we apply onto the object to cause acceleration, is proportional to the object's mass and to the acceleration, okay? Here you can see that the higher or more acceleration you have, more force you also have, right? Force and acceleration are directly proportional to each other. However, mass is inversely proportional to acceleration, meaning that, the heavier the object, then less acceleration it will be, right? So in this example that I am showing here, so in the first situation, there is only one person. So mass, let's say you have only one mass here. So you need to do a certain force here to actually move the bicycle, right? Ignoring the air resistance and whatever other resistance. But here, when you add your mass plus the mass of a second person, then the force you need to apply has to be greater for you to accelerate. So as you can see, mass and acceleration are inversely proportional to each other. Okay, we're gonna do a calculation of this, and I think there are some exercises in the book as well that I recommend you going there and taking a look at it, but there is one example I brought here in this class. The idea here with discussing about mass is because sometimes in our day-to-day life we use these two words, weight and mass, kind of interchangeably, right? But they do not mean the same thing, because mass is actually a measurement of inertia, is the amount of matter. We're measuring how much force you need to put in that object to make that object move, how many meters, whatever many meters you want to move. So mass is a measurement of the inertia. However, the weight is actually the gravity acting on that mass, okay? So for instance, what does that mean? So when you say that, oh, my weight is, 150 pounds, you're actually saying that your mass is 150 pounds, right? Because that is your inertia. That is you stopped on top of that scale without moving anything. But if one wants to push you out of that scale, then they need to put some force that is proportional to the mass and, to the acceleration to make you move out of that scale, right? But if you are talking, we are here on Earth, we talk actually about the weight, which is the gravity of, existing here on Earth acting on you. And with that, we can use the simple equation that force equals mass times acceleration, and replace that by W, where W is the weight, mass will be your measurement of inertia, and your acceleration, we're going to replace that for gravity. So if you actually want to know your weight, you do need to multiply your mass that you see on a scale times 9.8, or to make it easier, times 10. You probably don't want to do that because that's going to scare you, right? Especially if you're on a diet or, crazy about weight, but don't get too obsessed about that. The idea here is just so you understand that weight and mass are different, different concepts, even though on the daily life we ended up using as if they were the same. But remember, mass is a measurement of inertia, right? How much force someone has to act against me to make me move, essentially. Whereas weight is, that mass times the gravity that's acting on you to on Earth, right? On the moon, that weight will be different, but your mass will be the same, right? Mass doesn't really change because that's a measurement of inertia, but the weight is is proportional to the gravity of the place that you are. So you can think that in each planet that we go, we probably would weight differently. In Venus, Mars, Jupiter is on the moon as well, right? Because each one of those planets have a different acceleration, a different gravity. Okay, let's make a simple example here, right? So what is the weight of a 60 kilograms person on the surface of Earth? We know that force equals to mass times acceleration. Okay, we can replace this force by W to represent the weight. Mass is 60 kilograms and the acceleration is 9.8 meters per second squared. Okay, so there should be, I'm going to use an approximate here, okay, somewhere around 600 newtons. Okay, that's going to be our unit for weight or for force. Okay, and I'm just replacing this for 10 just because I don't want to use my my cell phone to calculate this, but you can do it on your own. Okay, the third and last law of motion proposed by Newton is that, for every action, there is a reaction, right? You probably heard that, from a friend that say, karma is coming for you or something crazy like that, but there is some truth in that. So Newton observed that, if you act on an object, that object will act on you as well. Meaning that if you push that object is also pushing you. So for all the action that you are, acting on that object, there is a reaction that is equal but opposite acting towards you. The way we can, describe this is by saying that whenever two objects interact, the force exerted on one object is equal in size and opposite in direction. Remember, force is a vector. It has a magnitude and it also has a direction, okay, to the force exerted on the other object. So for instance, here we have an astronaut pushing the satellite. you can imagine that, you know, the astronaut is pushing the satellite, but the satellite is also pushing the astronaut. The force that the astronaut is pushing, you know, the object, the satellite, is proportional to the force the satellite is pushing the astronaut, but they have opposite directions. Okay, as if, you know, you can do this very simply just by, you know, pushing yourself against the wall probably, and you will see the same. So now let's do one exercise about it. How about that? Okay, so here's our example. So you have a 60-kilogram astronaut in freely floating in space and pushes on a free floating 120 spacecraft with a force of 30 newtons for 1.5 seconds. The first question is, compare the forces exerted on the astronaut and on the satellite, okay? And then compare the acceleration of the astronaut to the acceleration of the spacecraft. For question A, we can actually, we don't need to do any calculations, right? Because by the third law that we just discussed, we can conclude that, you know, the force that the astronaut pushes the satellite is the same that the satellite pushes the astronaut, okay? So they are both equal to 30 newtons. What is different between those two forces? The direction, right? Because one is pushing the other. And by the third law, we know that for every action, there is a reaction that is the same in magnitude, but opposite in direction. So force for both, and I think it's already represented here, is the same. What is different is the direction. Okay, so A, very simple. How about B? How can we calculate B? Well, for calculating B, we're going to use Newton's second law. We're going to do F equals mass times acceleration for the, let's do astronaut, and let's do this for the satellite, okay? And you can ask me, well, professor, isn't like the acceleration 9.8? No. Why is not? Because they are in space, right? So there is no gravity in space. So we can actually calculate the acceleration here, and you will see that's going to be different from 9.8. All right, so how do we calculate the acceleration? Acceleration would be, we can work around these formulas, right? So if I have, let's do the astronaut first. So force is 30. The mass of the astronaut is 60 times acceleration, which is what I want to know. This is going to be 30 over 60 equals to acceleration. This is going to be, you know, 3 over 6, which is also saying 0.5 meters per second squared. That's the acceleration of the astronaut. How about the acceleration of the satellite? Well, we can see that the acceleration would be the mass over force of the satellite. So acceleration would be 120, sorry, will be, it's going to be the opposite, sorry. It's going to be force, mass, and this is going to be 30 over 120. So this would be 3 over 12. Is this 0.25, I guess, right? Okay, so you can see that the acceleration of the astronaut is twice as big or twice as much as the acceleration of the satellite. And why is that the case? Why is the astronaut accelerating faster than the satellite? Because the astronaut has a lighter mass, right? So astronaut has a smaller mass, okay? Now that we know the acceleration, do you guys think we can calculate the velocity? Because I gave you the time, so what would be the velocity of these guys, of the astronaut and the satellite after 1.5 seconds? And I know I'm not asking for that in the question, but I think it would be cool to see that, right? So I know that, let's see, I know that acceleration equals to, what's that? That is velocity over time, okay? So let's calculate for the astronaut force. Acceleration for the astronaut was 0.5, okay? Velocity over time was 1.5. So we have 0.5 times 1.5. Velocity would be 0.75 meters per second for the astronaut. Is that all right? I think that's correct. Okay. How about the same thing for the satellite? So delta V, delta T, we can do, this acceleration was 1.25, right? This is going to be times 1.5 equals v of the satellite. So this should be, and I can't do, this should be 0.25 times 1.5. That's 0.375. Okay, so that's the velocity of the, we forgot the unit here. That's the velocity of our spacecraft, right, of our satellite. So from that very simple type of exercise, we were able to calculate the forces, deduce what would happen with the forces based on the third law of motion, and then we could also calculate the velocity of each object, okay, after 1.5 seconds. Okay, to finish our class for chapter number 2, I want to talk about forces and circular motion, because that's kind of like gives an idea for Newton's law of gravitation. Okay, so there are two types of force that are acting when an object is accelerating in a circular motion. Okay, so the force that we just talked when we discussed about the second law was that force applied, you know, in a horizontal motion or in a vertical motion, right? But if there is a circular motion, there is also two types of forces that will be acting on that object. One will be the centripetal force, and the other one is the centrifugal force. So centripetal force is when the force is acting towards the center of the motion. Okay, so let's think that I am here in the middle of this circle, and I am, you know, I have a ball connected to a thread, and I am moving this thread above my head in a circular movement. Okay, so the force pulling the ball towards me is called centripetal force. However, there is a force acting in opposite direction, pulling the ball out of this circular path that I am making, right, as I am spinning the ball above my head. And that is called the centrifugal force. So how do I remember which one is moving into the center and which one is moving outside of the circle? Well, I remember of the F. F will help us remember that this is a flight, right? So it's flying away, essentially. So centripetal means coming towards the center. Centrifugal means away from the center, right? And Newton will propose that this force, actually, the acceleration of this object, you know, moving in a circle, is proportional to its velocity, okay, to its speed, to its square speed, but it's inversely proportional to the radius of that circle, okay? Meaning that if the radius increases, then acceleration decreases. And you can kind of do this testing, right? If you try to spin this ball around, the more, if the cord, if the thread is really big, right, the acceleration will be very small. But if you bring that thread closer to the center, then the acceleration will be much faster, right? So you can actually test yourself, right, and prove yourself that is the case. But knowing this, we can actually replace this knowledge with what Newton had previously described, that force is proportional to mass times acceleration, right? If I know the acceleration, if I know the acceleration is given by this, acceleration in a motion, in a circular motion is given by this formula, then I can replace acceleration here and actually come up with how I can calculate the centripetal force, okay? Why is that important? Well, this helps us to come up with this idea that there is forces acting, you know, one object will always act on another object. There is always an attractive force between masses in the universe. So for instance, Earth has a force acting on the moon, and the moon has a force acting on the earth, okay? And that force is actually proportional to their masses, meaning that bigger the masses of these objects, higher is the force, you know, greater is the force, but is inversely proportional to the distance squared of these objects, meaning that the farther away these objects are from each other, the lower this force is. Okay, so moon is acting on Earth, Earth is acting on moon. Same way if I was representing the sun here, right? So the sun is also acting on Earth and Earth is also acting on the sun. But as you can imagine, the mass of the sun is much greater, let me replace with S, than the mass of Earth. Okay? So it's much greater than the mass of Earth here. So of course that the force that the sun is acting on Earth is much greater because the mass is greater. Okay, and this is actually given by this law of gravitation, right? Newton will propose that every object in the universe is attracted to every other object in the universe with a force that is proportional to the mass, to the product of their masses, but inversely proportional to the square of their distance, to the distance between them, times this constant, okay, constant called g. Like I said, if we think that this is the sun and this is the earth, okay, each one of them are acting on each other, they are attracting each other, but as you can imagine, the sun has a much greater mass than the earth has, right? So the force here would be incredibly greater compared to the force that the earth acts on the sun, right? So why am I saying that? I'm saying that because, you know, the sun is so massive that the force that it's acting on Earth, it's actually pulling the Earth in its orbit. Okay, so that's why we, as the planet Earth, in the planet Earth, you know, are revolving around the sun because there is a force. The sun is actually pulling us, and not pulling, right, but keeping us in this orbit because of its massive size, and that causes this force here to be really great. Okay, the same thing works for the Earth and the Moon, right? So the mass of the Earth is much greater than the mass of the Moon, so that keeps the Moon in orbit, in the Earth's orbit. Okay, so just so you know how the universe works, essentially, the farther away, and you can ask me, but Carlos, let's think about planets such as, you know, Jupiter or Saturn that are really far from the sun, right? So if they are really far, you can ask me, well, the distance will increase. And that is right, the distance will increase. However, the mass of the sun is so great that the distance, it's kind of irrelative for this scenario. Okay, so that's why planets such as Jupiter or Saturn, Uranus, you know, even though they are so far from the sun, they are still kept in this orbit of our solar system because the mass of the sun is really great. So the force that the sun is acting on every other object in the solar system is really great. Okay, so I think that was it for this class. I know that we talked about lots of different things, but for chapter 2, this is it. We still have chapter 3 and 4 for this week. Okay, thank you so much.